Hi, hello everybody. Today we're going to be looking at our review here for the chapter 10, probability. Yeah, probability. All right, so the first couple of problems has to do with this Venn diagram here. We need to, or this information here, we need to create a Venn diagram. Hmm, Need these circles to be a little bit bigger, I think. Oops. Okay. All right, so what we know, 80, so surveys are class about their siblings. 80% students have a brother. We'll call this one brother, call this one sister. 75% have a sister. 60% have both a brother and sister. So we'll start with the intersection, which is in here, brother and sister, 0.60, 60%. Next, we can fill out how many students have a brother. 80% have a brother, but we already have 60% accounted for, so 20% here. Same thing with sister. 75% have a sister. We already have 60% accounted for, so 15% remaining. And we do need to fill out the rest of the sample space because this needs to add up to 100%. Currently, 0.2 plus 0.6 plus 0.15, this only adds up to 95%. So there is 5% on the outside, 0.05, that do not have brother or a sister. Now we can answer questions about the different probabilities. Remember, these are probabilities. They need to be a ratio, a decimal. So first we have the probability of brother or sister. This is the union. So the union can be found from the Venn diagram by adding these together, or you can find it from the information by adding 80 and 75 and then subtracting the intersection 60. Either way, we get 20% plus 60% plus 15%, so there's a 95% probability that they have a brother or a sister. Brother and a sister, this is simply the intersection, which we already can see is 60%. The probability of the complement of brother and sister. Okay, so we need to look at the brother and sister, which is 60%. Then we need to look at the complement, which is everything else. So 60%, everything else would be 40%. So 40%, that's the complement of brother and sister. People who do not have a brother and a sister. Uh, Lastly, we need the probability of the complement of brother or sister. So brother or sister was 95%. That's this, this, and this. The complement would just be everything else, which is just people who don't have any siblings, which is 5%, 0.05. Okay, number 5. Suppose that out of 800 cars parked at the beach, 220 are compact, 150 are blue cars, 75 are both compact cars and blue. What is the probability that a car selected at random would be compact or blue? So that's the probability of compact or blue. So we'll do the probability of compact plus the probability of blue, and then subtract the intersection, compact and blue. So compact, 220 over 800. Blue is 150 over 800. The intersection, 75 over 800. Okay, so we got 220 plus 150 minus 75, so 295 over 800. And then you can simplify that in the calculator, 295 over 800, 59 over 160. Number 6, a coin is tossed and a die is rolled. What is the probability of the coin landing on tails and rolling a number greater than 4? So we want probability of tails and greater than 4. Okay, well, these are independent events because or we can assume they're independent events, but they are because because tossing a coin has no effect on rolling a die. So we can just do the probability of flipping tails, coin landing on tails, multiplied by the probability that the die is greater than 4. So landing on tails, that's a probability of 1/2. Greater than 4, so you got 5 and 6 that are greater than 4 on a 6-sided die. So that's 2 out of 6, or 1/3. So 1/2 times 2 out of 6, that's 2 out of 12, which is 1/6. There's a 1/6 chance that this occurs. Landing on tails and rolling a number greater than 4. You can actually list out the sample space to take a look at this as well, because you can see all the probabilities: head 1, head 2, head 3, head 4, head 5, head 6. You can also have tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Okay, so 12 total possibilities, and of those 12, tails and greater than 4, there's this one and this one, 2 out of 12, which is 1/6. So you can show the sample space to calculate what this is. Let's see. Number 7, a bag of marbles has 4 red, 3 blue, 2 yellow, 4 green. 3 marbles are drawn randomly from the bag one at a time and not replaced. Find the probability that the first one is red, and the second one is red, and the third one is yellow. So these are dependent events. Each marble that we pull afterwards depends on the marble you pulled before it. So we do have conditional probabilities here. So we just need to multiply all of these probabilities together. So probability, first one being red, is 4 over 7, 8, 9, 4 over 13 times the probability that the second one is red. So now there's only 12 marbles and there's 3 red ones left, so 3 over 12. And then the probability that the third one is yellow, so there's 11 marbles left, 2 of them are yellow. So this is what we end up with. So 4 times 3 times 2, so we have 24 over 13 times 12 times 11, which is 1716. And then we can simplify this in the calculator. 24 over 1716, 2 over 143. There is a 2 over 143 chance that you pull out the marbles in this way. Okay, suppose that it is known 60% of high school students are Harry Potter's fan, 40% are Twilight fan, 28% are both. Are these events independent? So we just need to show, in order to show that they're independent, we just need to show that the probability of them both happening, Harry Potter and Twilight, is the product of the probability of them happening individually. Probability of Harry Potter multiplied by the probability of Twilight. Okay, so I'm going to take the Harry Potter probability, 0.6, and multiply that by the Twilight probability, 0.4, and I get 0.24, which is not the 28% that I was looking for. It's 24%, not 28%, so these are not independent events because this formula does not calculate the probabilities properly. One of these should have been conditional. Okay, so for the next couple, we have our frequency table here. If a randomly selected person is a senior, find the probability that they are female. So this is probability of female given that they are a senior. Okay, so we can find that by doing the probability of female and senior and dividing that by the probability that they're senior. So female and senior, 7 over 25. That is divided by the probability of senior, which is 17 over 25. Okay, which is 7 over 17. So the conditional probability, student selected as senior, find the probability that they're female. So female, given that they're a senior, 7 over 17. And you can see that because out of the 17 seniors that you have in total, 7 of them are female. Probability of a junior given that they are a male. So probability of male and junior, so that's 5 over 25, divided by the probability of just the males, so 15 over 25. So that's 5 over 15, or 1/3. And you can see that in the table because if you're given that the person is a male, then the entire sample space is only 15 people. Of those 15 people, how many of them are juniors? 5 of them. 5 over 15, which is 1/3. Probability of female or senior. So that's the probability of female. So 10 over 25. Plus the probability of a senior. So 17 over 25. However, we have to subtract the people that are females and seniors. They got counted twice. So right here, 7 over 25, these people got counted twice. So that's 20 over 25, or 4 over 5. Probability of male and senior, well, this is pretty straightforward. Just look at male and senior. There's 10, so 10 over 25, which is 2 over 5. Number 12, or 13, I mean, probability that a randomly selected person is male given that they are a junior. So this is the probability of male given they are a junior. Okay, so we need the probability of male and junior. So male and junior, so 5 over 25. Divide that by the probability of a junior, so 8 over 25. All right, so we get 5 over 8. That should make sense because if you look at just the sample space of the juniors, there's only 8 of them. And of those 8, how many are male? 5 of them are male, so 5 over 8. Okay, it looks for this next one, we need to actually fill this out. Survey of 200 students, so the total of all totals, 200 students, revealed that 130 prefer classical music when studying. So 130 of them preferred classical music when studying. In addition, 50 indicated that they are left-handed. So left-handed people, there's 50 of them. Of those surveyed, 13 said they are left-handed and do not prefer classical music. So left-handed and do not prefer classical music, so 13. Okay, so we have plenty of information here to fill in the rest of this table, I think. So we're missing this one. This needs 70. 130 plus 70 is 200. We're missing this one. This one's 150. 50 plus 150 is 200. We're missing this one. This one should be 37. 37 plus 13 is 50. This one should be 57. 13 plus 57 is 70. And then we're missing this one. Should be 93, because 93 plus 37 is 130, and 93 plus 57 is 150. Okay, so just check to make sure all of your totals add up the way they should. So 37 plus 13, 50, 93 plus 57, 150, 130 plus 70, 200. Also check the rows as well. 37 plus 93 is 130, 13 plus 57 is 70, 50 plus 150 is 200. Okay, so my table is fine here. Let me go ahead and put it in here so I can answer the questions. Given that a randomly selected student is left-handed, so given they are left-handed, what is the probability that he or she does not prefer classical music? So not classical given that they're left-handed. So we need the probability of not classical and left-handed over the probability of just left-handed. So not classical and left-handed, they're 13 out of 200. And a denominator probability of them being left-handed, 50 out of 200. So that's just 13 over 50. And that should make sense because if we're given that they are left-handed, there's 50 of those. How many of those 50 do not prefer classical music? 13 of those 50 do not prefer classical music. A randomly selected student prefers classical music. So we are given that they prefer classical music. What is the probability that he or she is not left-handed? So not left-handed, given they prefer classical music. So we need, in the numerator, we need the probability of not left-handed and classical. So not left-handed and classical, that's 93 over 200. In the denominator, the probability of just classical, so 130 over 200. So we get 93 over 130. I don't think that, well, maybe that does simplify. 93 over 130, it does not. Okay, and that should make sense because if we're given that it's classical, then we're just talking about these 130 people. Of those 130 people, the ones that are not left-handed, there's 93 of them, so 93 over 130. You're asked to make a password that consists of 4 letters and 2 digits. How many passwords can be created if repetition of letters and numbers is allowed? So 4 letters, 2 digits, and then we just need to go through and see how many different ways we can do this. So we need how many different options we have for each letter and digit. So 26 options for each of the letters, since we are allowed to repeat the letters. And then for the digits, there's 10 options for each of those. So 26 to the 4th multiplied by 10 squared. 26 times 26 times 26 times 26. Times 10 times 10. So a pretty big number. 4, 5, 6, 9, 7, 6, 0, 0. So 45 million of these can be done. Consider drawing a single card from a deck of cards. Event A is drawing an ace. Event B is drawing a spade. Prove whether these events are independent or not. So there's a couple of ways to do this. We can show that their conditional probability is the same as their actual probability. So we can show that the probability of A is the same as the probability of A given B, or we can just show that the probability of both events is equal to the probability of each event multiplied together. And that's probably going to be the easier way to do this. So the probability of A is, so event A is drawing an ace. There is a 4 out of 52 chance of drawing an ace. Event B is drawing a spade. There's 13 spades out of 52. And then we know the probability of drawing an ace and a spade because there's only one ace of spade. It's 1 out of 52. Now let's see if this formula calculates the correct probability. So probability of A, 4 over 52, multiplied by the probability of B, 13 over 52. And this actually does give us 1 over 52, which is the probability of them both occurring, 1 over 52. So these are independent. These are independent events. Drawing an ace has no effect on drawing a spade, and vice versa. Number 18, a single die is rolled. Let event A be rolling a 3. event B be rolling an odd number, prove whether these events are independent or not. I'm going to do this the same way I just did. The probability of A rolling a 3, that's 1 over 6. Probability of B rolling an odd number, that's 3 over 6, or 1/2. And the probability of A and B rolling a 3 and rolling an odd number, well, that's technically just rolling a 3, that's 1 over 6. Now let's see if this formula, probability of A and B, works out for this problem. Probability of A multiplied by the probability of B. So the probability of A is 1 over 6, probability of B is 1/2, so the probability of A and B is 1 over 12, which is not the actual probability of these two events occurring together. The actual probability is 1 over 6. Rolling a 3 and rolling an odd is 1 over 6. But calculating their probability gives us 1 over 12. So these are not independent. You can also show these independence by comparing the probability of the event to the conditional probability of the event. So for example, probability of A rolling a 3, or sorry, and you can calculate the probability of a conditional event by just the probability of them both happening over the probability of what's given. So if I did it this way, the probability of them both occurring is 1 over 6. The probability of just event B is 1/2. So I get 1 over 6 divided by 1 over 2, which is 1/3. A 1/3 is the conditional probability A given B. This is not equal to the probability of A. Probability of A was 1 over 6, not 1 over 3. So the conditional probability of A given B is not equal to the probability of A, which means these are not independent. So that is another way that you can show that these are independent or not. That can also be done with number 17. Number 19, how many different ways are there to award first, second, and third place from place prizes for a marathon from 10 total runners? So this is a permutation because the order is important. We have 10 elements. We want to permutate 3 of them. So this is n factorial over, so remember NPR, n factorial over n minus r factorial. So 10 factorial over 7 factorial, which is just 10 times 9 times 8. 10 times 9 times 8. Which is 720 different ways to do this. How many 5-card poker hands are possible given a regular deck of cards has 52 playing cards? Okay, so this is actually a combination because poker hands don't change. The order of the cards in your hand doesn't change. It's the same poker hand, so it doesn't matter what the order is. So this is a combination. So remember the combination, NCR, n factorial over n minus r factorial times r factorial. Okay, so we have 52 cards. We want to choose 5 of them. So this is 52 factorial over 52 minus 5 factorial times 5 factorial. Okay, so 52 factorial over 47 factorial times 5 factorial. All right, you can put this in a calculator. You can also put the combination in a calculator, 52 choose 5. This gives us 2598960. So 2,598,960 different poker hands, where the order does not matter. All right, that is it for our review here. All right, good work.